Okay, I'll start with you this second video regarding the line parameters. So line parameters. In line parameters, we want to determine number one, what is the inductance and resistance, and what is the capacitance. Okay, so this is shunt and this is series. So in other words, what we have, a resistance R, inductance L, and the capacitance. This is basically the parameters. So L equal what, C equal what, and R equal what. Okay? I want you to read the notes regarding these parameters, okay? And I will try to describe other things that may not be obvious to you. If we start with series, let's say impedance, okay? Let's say first, what is inductance, okay? Inductance. You go through the notes, you'll find it's very easy. Since this is the transmission lines 3, okay? So this is sort of lines. You may have a neutral here and neutral, okay? Or no, or not have it, okay? So in general, this line here, or this line here, will give you an L phase equal phase, inductance matrix. This phase inductance matrix, say LS, LM, 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 LS, LM, 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 and LS, where LS is self inductance, okay, and LM equal mutual inductance. How we calculate LS and LM is very easy, okay. I want you to read the notes and find out from the notes how we calculate LS and LM. And then we have L sequence, which is equal L0, L1, L2, and 0 here, 0 here, 0 here, 0 here, 0, 0. So L0 equal LS plus 2LM. And we call this 0 sequence inductance. Okay, and then we have L1 equal L2 equal LS minus LM. So knowing LS and knowing LM, we can obtain L1 and L2 and L0. So this is known as L1 equal positive sequence inductance, okay, and L2 equal negative sequence inductance, and L1 equal L2. Okay? So usually for the static elements, we have the positive and negative are the same. Okay? Now, knowing this, يعني from L phase, i.e. function of LS and LM, we can obtain L sequence. And knowing L sequence is a function of L0, L1, L2, we can obtain L phase. How? We know that LS plus twice Lm equal L naught, and Ls minus Lm equal L1 equal L2, of course. It's the same. So if we add them, if we subtract these two equations, we obtain 3Lm equal L naught minus L1, right? So Lm equal 1/3 of L naught minus L1. Okay, so we can obtain Lm knowing sequence inductance matrix, means knowing L naught and L1, we can obtain Lm, okay, and vice versa. So if we multiply the second equation by 2 and add them, so Ls plus 2Lm plus 2Ls minus 2Lm should equal to L naught plus 2L1. Okay, so this will give you 3Ls equal L naught plus 2L1, which means Ls equal 1/3 L naught plus 2L1. Okay, so if we know L naught and L1, we can obtain Lm and Lx. So if we know L phase, we can obtain L sequence. If we know L sequence, we can obtain L phase. Okay. Now, if we go back to, if we go through your notes, you'll find that we have three-phase system. Phase. Okay. This is three-phase. And try to find out what is L. Okay, we find Ls, Lm. I won't calculate Lm and Ls. I will leave it to you. It's in the notes. Okay, but let's just let me mention what is L naught and what is L1 equal L2. You will find that you have it in the notes, okay? L naught is L1 and equal L2, it's 2 times 10 to the minus 7 ln D equivalent divided by R conductor prime. So R conductor prime is RC times e to the minus a quarter, okay? And this RC is the conductor RC equal conductor radius, okay? It is in the notes, okay? And this will give you, the unit will be Henry per meter, okay? That's how the units will be in Henry per meter. However, L naught depends on the Earth. You see, L1 and L2 does not depend on Earth. L naught is equal 2 times 10 to the minus 7 ln natural log dE to the power 6 divided by RE bar to the cube RC bar D equivalent square. Okay, so you have it in the notes also. What is RE? Is equal RC, so RE equal RC bar. Okay, RE is the Earth. This represents Earth return. Okay, so we assume that if you have 3 currents here, okay, the loop, we assume that we have Earth return. So if the sum IA plus IB plus IC will come to IE. Okay? Alaykum salam. So they will add together in the Earth. This is the Earth. And we assume that we have an Earth return. Okay? And what is dE? dE is equal to 658.5 square root of rho divided by F, where F equal frequency and rho equal Earth resistivity. Okay, so the Earth resistivity affects the zero sequence inductance, but it does not affect the positive or negative zero sequence. So here we have no neutral. So even if you don't have a neutral, but still the Earth will affect the zero sequence inductance. Okay? Now, how we calculate a resistance? Okay? The resistance, still we have R phase. From this, we get R sequence. Okay? R phase is equal RS self, Rm mutual, Rm mutual, Rm mutual, RS, Rm, 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 and RS. So RS equal R conductor plus RE. So this is conductor resistance. RE, Earth resistance. Okay, and Rm equal Re. So R sequence is equal R naught 0 0 0 R1 0 0 0 R2. So R naught will be equal to RC RC plus 3RM. Okay, RE, 3RE, sorry, after this, RE. And R1 equal R2 equal RC. Okay, you find out easily from that. Okay, now if you look at this, R naught actually is equal RS plus twice Rm, and this equal RS minus Rm. Always when you try to obtain sequence, the positive and negative is self minus mutual, and the zero is self plus twice the mutual. Okay, this if we have no F. If we have F, if we have a neutral wire, and sometimes we call it earth wire. We have an earth wire. This is the conductors ABC, and we have here earth wire. Actually, the earth wire can provide a return. We can consider it as the neutral line, and also it provides some of protection against over high voltage coming from clouds and so on. Okay, so these are provided to protect the transmission lines, and we can use them. So this will not affect L1 and L2. It will affect only the L0. Okay, having that, it will affect only L0. I want you to see, it's, in the notes it's there how we calculate Z naught and Z1, okay, and Z2, okay. In that case, what we have, Z phase equal ZS, ZM, 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 ZS, ZM, 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 and ZS, okay? And once we obtain this, we can obtain simply Z naught 0 equals S minus Zm mutual and plus, sorry, this is Z1, this is Z1 and Z2, okay? So Z1 equals Z2 and Z naught equals ZS plus twice. It's always like that. So once we know ZS and Zm with a neutral wire or S wire, we can calculate that easily, okay? You will be having it in the notes. I want you to go through the notes and find out how we calculate these parameters, okay? It's very easy, okay? So I won't just define them here. You have them in the notes, okay? So now if we have a neutral wire, then neutral wire, neutral or earth wire, okay, affects only Z naught, okay? It does not affect Z1 or Z, okay? Now this is regarding series impedance, okay? If we go to the shunt admittance or capacitance, it's the same. For the shunt admittance, we define K phase as C phase inverse, the inverse of the phase, which is K self, K mutual, K mutual, K mutual, K self, K mutual, and K mutual, K mutual, and K self, okay? Once we have this one, we can calculate what is K. The sequence will be K naught, K1, and K2. 0, 0, 0, 0, 0, 0. Okay? Why? This is an inverse, C phase inverse. So this will be what? C sequence inverse, which is equal 1 over C naught, 0, 0, 0, 1 over C1, 0, 0, 0, 1 over C2. So we can calculate C naught and C1 and C2, okay? It turns out to be that C naught, 1 over K naught, is equal to 2 pi epsilon naught divided by ln HS times, okay, HM squared divided by RC times D equivalent squared. You have them on the notes, okay? So this is the zero sequence capacitance. You see, H depends on the ground, on the distance between conductors and the ground. What is the level of the conductors related to ground, okay? And C1 equals C2 equal 1 over K1 equal 1 over K2. And this is equal to 2 pi epsilon naught divided by ln D equivalent divided by radius of conductors minus ln HM divided by HS. Okay, you know how to determine HM and HS is very easy. Okay, just look at it. Now you have these conductors here, A, B, conductor A, B, and C, and this is ground level, and we have an image. This is A, B bar, A bar, and C bar. This is conductor images. Okay, we have an image for each conductor, so the electric field will come from the real conductor. So see, what is the level, the height of conductor? Say it is equal, for example, HC, then here you will be having also HC. So if you have the height is 20 meters, it means the distance between the conductors and the image will be twice that times that height. So if it is 20 meters, this distance will be 40. If it is 30, it will be 60, and so on. We name this one here as H11, and here as H22, and here as H33. Okay, and this here is H12, 1, 2. This here is H23, and this distance here is H13. So simply HS itself is square, is the cube root for H11, H22, and H33. Look at the example in the notes also, and there's an example how to calculate these things. And HM mutual is again cube H12, H23 times H13 cube. Okay, so it's very easy to determine. We look back to this here. So HM and HS, the C1 and C2, the positive sequence, of course, the zero sequence depends on HS and HM. The positive sequence also depends on HM and HS. Usually HM greater than HS. Okay, that will try to increase the capacitance. So if we want to neglect the earth effect, okay, ln HM over HS approaches zero if we want to neglect earth effect. We set this, okay? If we want to neglect the earth effects, we set this here to zero. And in reality, it is zero ln HM to HS approaches zero if HM approaches HS, i.e. if the conductors are very far from ground. Okay, so when the conductors are several hundreds of meters from ground, then H11, H22, H3 does not differ too much from H12, H23, and H13. So approximately HS will equal to HM. So if we take the conductors very far away, if these conductors are very far, okay, then if these conductors are very far, then what we have, these conductors are very far, then the earth effect will be negligible, okay? Its effect will not be noticed. So this basically how we calculate inductance and capacitance. Taking into consideration earth lines, we take also earth lines into consideration. Say this is the earth, okay, and these are the conductors A, B, C, and this is the ground level. Then we take the image of these conductors here. This is the image, and this is the image of the earth wire. So this is earth wire image, okay, and these are conductors image, okay, earth and conductors, okay, earth wire. We do the same. We can calculate HS, we calculate HM, and we have HN, and we have HNN. You have them in the notes, okay? And from the notes, you can easily calculate the zero sequence and the positive sequence impedance, okay? Now, you should go to the notes, okay, and find out when we have an earth wire, how it will change little, okay. Having an earth wire, an earth wire shall not change C1 and C2. It only changes the zero sequence, C naught only, okay? So I want you to check out from the notes how the effects of having a neutral wire affects the zero sequence, okay? It's very important. So here you will need an HN and you will need a DN, and you have them in the notes. What is DN? This is not DN here. Let me just correct this. Here you need a DN, okay? DN equal what? All these depends on, for example, if you looked at A, B, and C, and here is a neutral earth, then you assume this is D1N, and this is D2N, and this is D3N, then DN simply is D1N times D2N times D3N. It's very easy, and you have them in the notes, okay? And similarly, what is H1N, HN is easily determined using that also, okay? What else? What we need also, sometimes in high voltage, we have what we call them bundled conductors. In bundled conductors, each phase are constructed as a bundle. Yani this is phase A, this is phase B, and this is phase C. So in this case, we need D equivalent. Say here is D1, and here is D2, 3, and this is D1, 2, and the distance here is D1, 3. So D equivalent equal geometric mean distance. Okay, geometric mean distance is is the root, the cube root of D1, 2, D2, 3 times D1, 3. Okay, what we need also instead of using RC, which is conductor radius, we need what we call them geometric GMR, geometric main radius. It's very easy to calculate. Okay, now we have geometric main radius L, and the geometric main radius C. This we use RC, and here use RC, here use RC bar, okay? If we take an example, if we have a conductor here, RC, and we have a distance D. So this is phase A, and phase says B and C, which means that phase A, B, and C consists of two conductors separated d centimeters or whatsoever, and has a radius, the conductor has a radius of RC. Then how we calculate the geometric main radius for C is equal, we have D times RC times D. How many times we have? The distance between this conductor and itself is RC. The distance between this conductor and the second conductor is D. The distance between the second conductor and itself is RC. The distance between the second conductor and the first is D. And if you look at how many multiplications we have, 4 multiplications. So this is a quarter, n squared. So this is RC squared, D squared, a quarter, it will be RC. Okay? This is for RC. For geometric main radius for L, we need just to replace RC with RC bar. Okay? So if we use the geometric main radius for inductance calculation, we use RC bar. If we use it for capacitance calculation, we use RC. So RC bar is equal RC times e to the minus a quarter. This is very important. So this is for 2 conductors. For 3 conductors, so this is D 1, 2, this is D 1, 2, 3, and this is D 1, 3. This is the bundle of a single phase, okay? This is a bundle of a single phase. And usually the conductors have the same radius. So what is the geometric main radius for C is, you start with this one, RC, times distance between itself 1, 2, and the distance within D 1, 3. Then times RC D 1, 2, D 2, 3 times RC D 1, 3, D 2, 3, D 1, 3, D 2, 3. We look at them here. RC, we start from the first conductor. First conductor is this one, RC. Okay, this is the first conductor, RC. The distance between the first conductor here, okay, let me just change the color. Okay, this is the first conductor, the red color. So the distance between this first conductor and the second one and the third one is D12 and D13. So RC D12, D13. We finish that, we go to the second conductor, which is this one. The distance between the other 2 conductors is this one distance and this distance. So that's D12 and D23. So RC D12 and D23. Then when we come to the last conductor, the third conductor here, okay, this is the distance and this is the distance. So it's D23 and D13, D23. How many multiplications? 3 and 3 and 3 is 9. So 1 over 9. Okay? Then this is the way how to calculate the geometric main radius of C, of L. Just we use RC bar times D12 times D13 times D12 times D23 times D13 times D23. okay? And this all to the power over 9. So just for inductance, we use RC bar instead of RC, okay? So this is the basic things I want you to learn from the notes. Read this video, watch this video, and read also the notes, okay? And then you prepare yourself for the test on the 21st April. It will be on these things, online parameters. It will be a multiple choice, okay? Read the notes, watch this video, and understand how to calculate geometric mean radius, for inductance, for capacitance, geometric mean distance, how to calculate zero sequence capacitance and inductance, how to calculate positive and negative sequence capacitance and inductance. This basically would be the material of test 1. Let's give it a trial. We'll be having several tests. So this first test concentrate on this line parameters, okay? Now, what we will do also, how we represent the lines, okay? It is in the notes. I want you to read the notes, and basically we have short lines, usually this less than 80 kilometers. We have medium lines, and we have long lines. Here we use approximation. We call it lumped parameters. While for long line we use exact. Okay, exact, it means we call it distributed parameters. Here we use exact. Exact means distributed parameters. Okay, so basically for the short line means that what we have inductance and resistance, and the capacitance is too small, so we can't neglect it. So we have just a series Z, okay? For medium, we cannot neglect capacitance. So what we do, we take L and R and we call it, this is Z series. But we divide the shunt admittance or matrix or shunt admittance, positive or negative or zero sequence, by 2. We put one of them at the sending end. We put the other half at the receiving end. Okay, and we call this pi model. Okay, we call it nominal pi model. For the long line, we use distributed parameters. It means something like this. It's distributed parameters. For each small length of line, we have a capacitance and a resistance. In the notes, you'll find what is Vs as a function of A. VR and IR plus B. IR and I sending A VR plus D IR. Okay? Here you have C. Okay? C. ABCD are named as this ABCD parameters, and we can calculate them easily. So for the short line, we have ABCD parameters. What is A, B, parameters. For the medium line, also what is the ABCD parameters. And for the long line, okay, long line, what is the ABCD parameters? You have them in the notes, okay? Now, for the long transmission line, we can approximate this long transmission line by a pi model, but instead of Z, we call it Z bar. And instead of Y, we call it Y bar over 2 and Y bar over 2. And we call this not a nominal, we call it equivalent. Equivalent pi model. Equivalent means it's not exactly the medium one, it is exactly the long one, but made similar to the nominal pi model of the medium. We call it equivalent, okay? Equivalent. So Z bar is a function of Z, and Y bar is a function of Y. It's easy. You can find it out in the notes. I just will write them to you here. Okay, have it. You have them in the note. Okay. Actually, Z bar is equal to Z times sin hyperbolic sin gamma L divided by gamma L. Okay. You read the notes to find out how you calculate gamma, which is the propagation constant, and how you calculate Z. This is Z per meter times length, total Z. So we use for the nominal Z, but for the equivalent model we use Z bar. Similarly, Y bar is equal Y times tan hyperbolic tan gamma L over 2 divided by gamma L. Okay, L over 2. Okay, so these are correction factors. So these are considered to be correction factors to correct from the medium to the exact or long. Usually short, we consider line short which is less than 80 kilometers, medium when it is greater than 80 but less, let's say, than length, let's say approximately 240 kilometers, and we consider it as long if the length is greater than 240 kilometers, such as 300 and so on. Okay, so you find them in the notes. How you calculate the ABCD parameters for each model is very important. Okay, and I want you to read the two examples. You have two examples at the end of the notes. I want you to read them and understand how we calculate the ABCD parameters, the impedance, the admittance, shunt admittance, pace matrix, sequence matrix, and so on. Okay. Then also I want you to read about the voltage regulation. It's very easy. You will not spend something on this video, but go to page 29 and find out the power flow through transmission lines. It's very easy. You can understand it from there. And I want you to understand the voltage regulation. So you read power flow at page 29 and um, voltage regulation at page 30. Okay, and I want to also to read something regarding compensation, VAR compensation, reactive power compensation. It's very easy. I won't spend time on this video. I will leave it to you. Also, reactive power compensation. We have series and shunt compensation. Okay, so it's at page 31 of the notes, okay, of the notes. You have them. I sent it before these notes to you through the WhatsApp group, and it is also available in the Blackboard. Okay, read these things, be prepared, and page 32 you have the example. Read it also. Yes, I'm just trying to find out that example. Yes, it's there on page 32. Read them. It is about also compensation. Okay, and an example two is very important. I want it, so it shows you how to calculate the A and ABCD parameters, how to use also compensations, and okay, it's very easy. I wrote these notes for you, so it's very simple. You can, and if you don't understand anything, just let me know. Okay. Okay. First. Okay. So you have them there. Now, what I will plan for you, I will. Now you have the first test. Be prepared for it. Read. It's easy, but I want to test your knowledge. Okay, and let's give it a try. It's just the first. Okay, how I will mark the course for you is you submit the assignments as per the due date. You submit also the project. I gave you a project. You have it there, and see the due date. You submit it by that due date, and we'll be having several tests. This is the first test, test number 1, on transmission line parameters. It will be 30 minutes the time, and it will start at 9 o'clock on the 21st of this month at 9 o'clock p.m. And you have 30 minutes, and you have 1 hour to log in. So after 10, from 9 to 10, after 10, you won't be able to write that test, okay? I made it 30 minutes. It's very easy. It's 10 question, multiple choice. Okay, read this, the note on line parameters, and let's practice this test as a practice. And if you do well, I will consider it for you. So try to prepare. If you don't do well, I'll consider it as a trial. Okay, so try to do very well. So let me consider it for you if you get good marks on it. So that's the first test. I will grade it as over 20 marks, but we'll be having several tests. Not only that, we'll be having another test on per unit and generators, synchronous generators, maybe a special test also on transformers. So we'll be having 3, 4, 5 tests, okay? Shortest 30 minutes, something like that, okay? And I will tune at the end your marks. I will decide how many on assignments, how many on the projects. Basically, I may consider 20 to 30 on assignments and projects. And that is 70 marks, 80 to 70, 70 to 80 marks would be on these tests. These tests are designed as tests and quizzes, both together. Okay, so short, I want to understand your knowledge acquired from this course. So if we make 4 tests, for example, 20 each, then that's 80. If we made 3 tests, 20 each, that's 60. So let's make more than 3, 4 to 5 tests, okay? And try from this first test to do very well, because it's very simple. I assure you, it is simple. Just what you need is just prepare well. Read the note on transmission line, okay? When you open your computer for the test, have notes. Some of the your notes is with you, but have some papers, empty papers, and a pencil, and try to calculate the things requested. Because for multiple choice, either you get the right answer or you get the wrong answer. Either you get 0 or 2. So we have 10 questions. Each one is 2. That's total 20. For each question, either you get 0 or 2. You don't get 1 or a half. Okay. So try to be serious in answering the questions. So what you need is a pen, a paper, and just don't be afraid. Don't fear the test. It's very simple. And as I told you, this is the first test. I want to make it a trial if you don't succeed in it, if you don't do well. If you do well, I will consider it for you. Okay? So you learn how to prepare for the test and how to write the test of multiple choice from this test. Okay? Then I'll talk to you later, and be prepared for this test. Thank you.